Hi everybody, this is an extension on the shot tower example we did in class the other day. So again, we have 1 millimeter diameter spherical liquid lead droplets falling from the top of a shot tower at 700 Kelvin into air at 300 Kelvin. So what we did in class is we looked at how long it takes for the droplets to cool down to their melting point temperature of 600 Kelvin, given that H is 100 watts per meter squared Kelvin. So that's what we did in part A. So this is what the droplet looks like. It's a sphere. Since it's lead, we know the values of rho, C, K, and we also know the initial temperature. We know H. We know the melting point is at 600 Kelvin. So we have all these things available to us, and we want to apply the lump capacitance approach. So we first have to calculate our BO number, which we did, and we found out that the BO number is small. It's less than 0.1, so we're good to go with using the lump capacitance approach. And so here then what we did is simply use the equation for lump capacitance to whittle things down to get our value of the time it takes for it to go from 700 down to 600. So the extension then we're going to talk about is in part B, is how long does it take for the droplets to solidify after they reach their melting point temperature. And then beyond that, C is then if we know the droplet speed, we'll throw 3 meters per second out there, we can see then how tall to make the shot tower so that the time it takes for them to do both the cool down from 700 to 600 plus to solidify would then be completed at the instant they hit the bottom of the chamber. Alright, now I have to point out that some of these numbers here, like the 3 meters per second, I think are off. They're just wild guesses for purposes of doing this example. Okay, so let's do part B. And I'd like to start by first drawing out what the temperature would look like. Let me get rid of that. What the temperature would look like in this versus time. So under regular lump capacitance, you start off at Ti, and you have T infinity, and you have an exponential decay. So here's what we would expect, and this could continue on like so, if it was regular lump capacitance. But what's really going on is that it's reaching our melting point temperature of 600 Kelvin. And at that point, it stays at a constant temperature. And then eventually at some point when you have the phase change being completed, then it would drop off again, down to 0. The idea behind this problem is that this point here, this time t, is going to be the absolute end time. We'll say TE. So this is the time, the total time it takes for it to start at time 0 to go all the way down to TE. Now we already found TF. So this is for part A, is what time at TF does it take to go from 700 Kelvin down to 600 Kelvin. And we use our standard lump capacitance relation for that. And then between TF and TE, which we'll call here delta T, delta TE we'll say, is the time that it's in the two-phase regime. It's solidifying, so the temperature is fixed. The temperature is 600 Kelvin. So what we want to do then is find out what is this time duration here. And we'll do so by applying our energy balance to ECV dt, is E dot in minus E dot out plus E dot gen. Here, we know that E dot in is 0, E dot out is Q convection, which is HAS T minus T infinity, and there's no generation. So the difference here is that we know that the energy in the control volume is, we normally write it as MC times time, as temperature T. That's what we did above. Or that's what we did in terms of deriving the lump capacitance expression. But here, T is fixed. What's changing in terms of the control volume is the fact that you've got phase change going on. So really here the energy in the control volume is going to be MH, I'll say sub SL, which is your latent heat of fusion. So it's basically the energy required to take a solid and to convert it into a liquid. And since we're going backwards, we're going from liquid to solid. It's the energy absorbed as the liquid droplet turns into a solid. So I would rewrite this whole thing here then as you start off here at the end at little te, and it's a solid, and we end up there, and we start off here at Tf where it's a liquid. So this would be delta T. On the bottom it would be delta Te, but let me do it this way. The whole thing put together, I would write it as mH sub Sl over delta Te. Okay, so in other words, again, we have a fixed temperature T right here. So this is just going to be 600 Kelvin. If we know T infinity is 300 Kelvin. So we need to get HSL, and so I looked it up. And the value that I was able to find online was about 23.0 kilojoules per kilogram. So we have everything we need, we just need to plug in the values that we had from before. So AS again is, well, maybe before we do that, we can reformulate it in terms of L sub C, so I'll do that. All right, so M is going to be rho V like we had before. So what we get is rho V H sub SL over delta TE is equal then to minus H A sub S T minus T infinity. So here you can see we have the minus sign in front of the Q convection. Now, again, going back up to here, HSL is the amount of energy you have to put into the system to get it to go from liquid to vapor, liquid to solid. Sorry, from solid to liquid. But here we have the other thing, the opposite going on. So I would say the more appropriate thing to do is put the minus sign here too, to account for the fact that we're actually the energy inside the control volume is going down if HSL is a positive number. So this way the two minus signs cancel out, and we can write out here that delta TE is going to be then rho V H sub SL over H AS T minus T infinity. Now V over AS again is L sub C, which we know is D over 6. If we go up here, we see that this is D over 6. So then finally, we can solve for delta TE. So it'll be rho D H sub SL over 6H T minus T infinity. Plug in some numbers here. It'll be 11,340 kilograms per cubic meter. We know the value of H sub SL is 23 kilojoules per kilogram, so we're going to make it, we'll account for that. So it'll be 23 times 10 to the third joules per kilogram, so make sure everything's in base SI, or else you're going to get yourself in trouble with the units. 6H is again 100 watts per square meter Kelvin, and then the difference between T and T infinity is 300 Kelvin. 600 Kelvin minus 300 Kelvin is 300 Kelvin. And what you get is 1.45 seconds. So this is how long it takes for it to solidify. And then for part C, you're simply going to say the total time, we'll say TE is equal to TF plus delta TE. If you go up, TF is 0.702 seconds. Let's say 0.70 seconds. Delta TE is 1.45 seconds. So then the height of the tower, L, is going to be the time times the velocity. So it's going to be 2.15 seconds times the velocity of 3 meters per second. That's how tall the tower would be. Again, this is kind of a canned example. Obviously, if we have more accurate values of that velocity, then we'd be able to get a better indication of what the height of the tower should be. And so that is it.